And you could even go worse and make them as lots of 8 of them as 2 LEDs and 8 pairs, and then you get 2.8 amps. But it might be useful if you've got a battery you're trying to run the whole thing from. You may not have 13.5 volts reliably. If it's a 12-volt battery, it's fine when it's fully charged, but when it's discharged, you've got 8 volts maybe. You run it like this, you can get 6.6 volts, you can run it from a battery. So it's still a good solution. Depends on what your application is. So this, again, the point is how you wire them up determines your electrical interface, but that's also determined by what power supply you've got available to power your LEDs. And I want to go next about dimming. There are only 2 ways to dim an LED. You either do it digitally, PWM, switching it on and off, or you do it analog. There are many ways you can control the dimming. So the difference between 1 to 10 volts, or DALI, or potentiometer, or PWM systems, or DMX, infrared, wireless LAN. We've got a demonstration here where I use an iPad as a controller to dim LEDs. So it's using wireless LAN link, and with this thing we can turn LEDs on and off. If you look at the back there, you can see I'm turning the LEDs on and off at the back line. I can change colors of lights. All with a slider control from an iPad. Say, wow, great, this is a really nice application, but what am I doing? I'm using PWM dimming for every case. By PWM, I mean pulse width modulation, just so you're clear of that. Basically, you're switching the LED on and off too fast for you to see. If it's half the time on, half the time off, it's half the brightness. Simple. If it's only 25% of the time on, most of the time off, it's going to look darker. That's why it's such a universal interface. And the nice thing about PWM dimming is it's digital, so it's very easy to interface to a computer or an iPad in this case. It's kind of linear-ish. I'll go a bit more about that with the next slide. It doesn't change the LED color. You get manufacturers like Cree making a very nice fixed color balance, and you want to make sure that when you dim it, the color remains true as you dim it. Very important. And the nice thing about PWM is that you can link very long cables together because it's digital. It's either on or off. So if the control signal is 0 to 5 volts, if it goes 0 to 4.5 volts, it doesn't matter. It will still switch on and off cleanly, even if the cable is 600 meters long or more. Disadvantage is that when you're switching on and off and you're using a camera, you see nice blurry interference bands on your camera. And if you're using it with moving images or anything you're illuminating is also moving, like a machinery, you've got a stroboscopic effect which could be quite dangerous. So, and the problem I said before, it's linear-ish, is because there's a reaction time of the driver. The LED itself will switch on and off very, very fast indeed. But because you're turning the driver on and off with the signal, there's a certain startup time. So, for example, what you see here is the control, and you see here the output signal, the current is flowing. That's true of any driver. And obviously, if you start making it tighter and tighter, you can see that it starts to become unstable because the driver can't stabilize itself before it's switched off again. So you'll find that the current is not accurate anymore. But if you do it right, you get a nice linear control, everything's fine. If you look at the other problem you see about this is this is a competitor from their website. You see that 100% and it goes down nice and linear to about 10% and then they just stop. They can't do that last bit. They don't tell you that. They just stop the curve there and say, oh, you don't need less than 10% dimming because they can't do it. It's not stable enough. We go right down to 0. And it's linear the whole way down. So these are actual test results. We've measured this. It's not just a nice graph that we've drawn a nice straight line. These are measurements, and that we do more measurements at the top and bottom to make sure we are absolutely linear. So we spent a lot of time to make it nice and linear and right down to 0. The other thing you do is analog dimming. Analog dimming is the second way of controlling the brightness of an LED. And in this case, what we do is we actually reduce the current. So if the maximum current was 350 milliamps, as you dim it down, you'd reduce it to 300, 200, 100. So we actually control the current flowing through the LED. It's nice and easy because lots of standard lighting controllers have an analog output as a control circuit. They'll say 0 to 5 volts, 0 to 10 volts, 1 to 10 volts. And it's nice and linear, actually, because the characteristics of an LED is that the brightness is very, very linear with the current that's flowing through them. So as you dim the current down, you get a very nice linear change in brightness. And it's very suitable for anything that's moving. For cameras, perfect. You don't see any interference patterns. The trouble is, though, you can at very, very low currents, the LED can change color because they're designed to run at full brightness. If you get down below like 10% dimming, they'll start either going bluish or reddish depending on the design. So I'll jump to the next one, which is thermal feedback. What's the best operating temperature for an LED? We've seen before in the previous presentation how you can decide this. You can type in the figure. But what is the best? That's where you have to decide yourself. Depends on your design. It affects everything else. You have to decide yourself what temperature are you going to allow your LED to run at. So what you can say is, okay, I'm going to design it for my absolute maximum amount of light that I can get out of it. My design says I need a lot of light, so I'm going to run it really, really full power, get a lot of light out. I don't know what's going to happen, though, if it gets too hot. It's going to burn. It's going to overheat. The lifetime is going to go down. It's not going to fail, but what you're going to get is nowhere near what you designed for your lifetime. So what you need to do is say, okay, measure the temperature of the LED. If it gets too hot, I'll start dimming it down, reducing the power to 90% power, say. So it's a dimming. So you need a dimming control input for your electronics, but it's not dimming 100 to 0% anymore. You probably need to go down to 100 to 75%, because all you do is taking the edge off the power that's going through the LED to allow it to run a bit cooler so it doesn't overheat. We said before we can use a thermistor for this. That's why it doesn't have to be so accurate. And the nice thing about a thermistor, if you look at the resistance with temperature, it's really non-linear. It's not a straight line. This is a log scale here and a linear scale with the temperature. So you can get ones which are at 50 degrees centigrade. They're about 100 ohms. You go up to 110, they're 1 mega ohm. So it's almost like a switch, but with a bit of linear, it's not a straight on-off switch, but it changes very rapidly at a certain temperature, a trigger point, so to speak. So it's very useful for us as a driver manufacturer to use that characteristic. You can build, for example, with our DC-DC converters, all you need is the thermistor here, a couple of other resistors to set up the point where you want it to change, and you get a very nice curve that at a certain point the temperature of the LED is dropped because the current is dropped. So it's easy. A couple of resistors. You can do the same thing with a light-dependent resistor. So this is very useful when you want to turn the light on when it gets to dusk. So you have the same amount of light illumination in an area. Typical application might be a hotel lobby. You say, all right, I'm defined that in the hotel lobby, I'm going to have a certain amount of lux level. When it's bright outside during daylight, you dim all the lights down or off. As it gets dark, automatically the lights come brighter, so it remains the same. quite a tricky thing to do normally, but with this, just light dependent resistor, one resistor, you're done. You can do it a bit more complicated. We have a project running in America, which is a professional LED luminaire, which uses optical feedback. So what you see here is the change in light level of different types of LED with the temperature of the air and the current flowing. So it changes over time. But it's not a nice change. It's not like a change that's a straight line. It goes up and down sometimes. So if you actually measure the light coming out of your luminaire, you can actually control that so it's absolutely the same every time. Why might this be important? You put in 4 lights. A year later, you build in a 5th light. And it looks completely different to the other 4 because it's too bright. You do something like this, all 5 lights look the same, even though the first 4 are a year older. Maybe at this level rather than at this level. Again, it's how you use it. So again, back to the whole point of this, solid-state light is a system of different elements. The electricity coming in, you've got the power interface, the drivers, the control, sensing, you want to make constant temperature or constant illumination, the thermal interface, the optical interface, the lenses. What you get out of it is light and some heat, which you have to get rid of. So get the right LED, you get the right driver, get the right heat sinking, right optics, right mechanical design, you have a successful light. So, any questions? I think best we save them for later. I've gone through fairly quickly, I know, but we'll give you copies of this presentation if you need it. So, hopefully that's helpful to you when you're designing your next solid-state light. Thank you very much.
Thank you, Steve.